This afternoon I'm my own chairman. So I will continue to prove this theorem, which states that if for a ancient solution of Ricci flow, then the scalar curvature is non-negative for all t and x. For t and for t. So I didn't mention that it is complete. During my lectures, the matrix is always complete. But in this case, the difficulty is when the manifold is non-compact. So in the last lecture, we have this formula. And also, if the Ricci curvature is bounded, the norm of the Ricci curvature is bounded above by a constant, then in the ball, then this outside the ball. So it is always possible to choose R0 when the interval is compact. So actually, this is not a condition. So so the proof is for any constant a bigger than 2, there exists a k a, which depends on a, positive, such that the scalar curvature is bigger than or equal to minus k a when it is 0. And x in the ball 0, 0, a. If you enlarge the ball, you have this. Sure, it's a limited ball. And we define a function. The idea is that we define a function, a cutoff function. Define u. U of x t equals to distant function d. I will not write the x0. Just don't repeat. Because it's clear that x0 is origin. Where phi is the function like this. It's 1. It's 8 or 7 over 8. It's 1. So we will see what this satisfies. We just do some computation. First, we have phi. We have r. We also have r minus plus phi. So we also have some mixed terms. That is, we have gradient phi gradient R. We also have some terms, the mixed terms. I will check it here. We have a second derivative terms. Right. So we can expand this term. We just use this is bigger than this one, and we need we have information for this kind of thing. So it is like R n over 2 over n phi r squared, and we have R. When we compute the first derivative, we have phi prime, which is phi prime R, because we have here a 0. D. This term. Additionally, we have a term a 0 square prime, because we have a gradient. Actually, we have a gradient t here, so we still have this term. We'll put here phi prime gradient d gradient r. So we have this is u. This because u equals this. If we put this kind of thing here, we can put a square here. So that's such that this is u squared. So we also have this. We can assume that there exists a point in x0, a r0, such that r is bar for some time t is negative here. So if it does not exist this kind of point, that means R is non-negative. That is exactly what we want. So we can choose a sufficient. If there exists a point on manifold, we can choose a big, such that this point is included. So we define a function u minimum of t is the minimum x m u x t. So at the point which realize the minimum point, we have derivative of u equals to 0 at this point. So actually we have gradient phi. I just write applying r plus phi gradient r. So that means we have gradient r, gradient d, sorry, gradient d, gradient r We have R somewhere. So it is equals to green R. That means, yeah, right. We have minus phi plane gradient d square R, which has a phi here. So this term can be replaced by a term divided by phi here. So finally, we can write down the d t u t. Since we have Laplace at this point is non-negative, also we know that at the point we have phi plane R is phi plane is negative, so it's non-negative. So we can apply this equality. So we have just square. I just put u square here. And minus 5, 3, 8, R0 square. Minus some constant R, because the phi is fixed. So we mix some terms. We just put here. This is a constant. The constant depend on only on n. Does not depend on a and R0. So here you have R. So we just use. We can combine this together, and we put the term out. So actually, it can be written down. We give a term here to him, and then minus ER0 square. See some here. If we put R somewhere, and you have a constant here. This is we put this out. This is a constant. So this is a constant like this. So we have phi here, and then we have less than or equal to c square and plus r square. We just put a constant alpha, 1 over alpha here, and such that we give 1 over n to him, and then we have this kind of bigger than or equal to minus. So this is it's a simple computation. So from this, we have this inequality of recurrent type. So of course, this the derivative is not a normal derivative. It's defined by Hamilton. You only take one direction from the positive side. So that is sufficient for us to prove the inequality. So this, if you analyze this one, if u is sufficiently negative, then this will become positive. So if u here is 0. So if we suppose this constant r0 minus square over c, if u goes beside this one, he will, because this derivative is positive, he will go back. So you can find a constant here such that u is bigger than this constant. So on the other hand, if u is not so big, so you have you can give some part here. For example, you give 1/2n part to this kind, to just let this one just like bigger than or equal to, for example, 2n u squared. So finally you can have u minimum of t is bigger than or equal to minimum. You can integral this one. You get minus 1/t plus ka, and I just put n here. I need n here. 2n here. Yeah. And you have, I just put n minus nc here, square. Where a is arbitrary. So if you net this kind of inequality holds for this interval. So you can replace t by t minus alpha. Replace t by t minus alpha, because they use the solution exists from minus infinity to a fixed point. So you have u bigger than minimum. Actually, this is constant. This alpha. Of course, here the constant square. So R A can goes to infinity. So this minus here, it goes to 0. And we can let alpha goes to minus infinity. So this goes to 0. So actually, for all alpha, we have u minimum of t bigger than or equal to 0. So this technique is actually first used by Li Yao in his estimate of heat kernel. I just want to say a few words about the corollary of this result, because it holds for ancient solutions. So it is also true for stellar soliton. So stellar soliton we also have non-negative scalar curvature. And from the maximum principle, if the manifold is not flat, R must be positive at every point. So the remark here, if G is not flat, R positive. Since I promised to Fernando that during the lecture I will put some problem here. So, can this result? Can you have a similar result for expanding soliton? It has been known that you can use this technique to estimate the scalar curvature for expanding soliton, such that the scalar curvature is bounded below by a constant with a fixed time. The constant depends on time. So this interesting thing that can you get some estimate? Can we get an estimate like for upper bound of upper bound for R. It seems that some of the proof can work for expanding solitons. I mean this kind of for all kind of solitons. So the upper bound may be possible for expanding solitons, but it's difficult for shrinking solitons. If get an upper bound for R. I mean usually the upper bound. We will see that the upper bound rough upper bound for R can be obtained by estimate the potential function of soliton. Okay. And the problem. So if there is no problem, I will go to a special case. That means a gradient shrinking soliton. Sometimes people call that as a shrinker. It's simple. Shrinker means a gradient shrinking soliton. So I will write down the basic formula here for a shrinking soliton. Shrinker means you have Ricci plus d squared f equals to some constant, positive constant. So I will fix like this. You can make a scaling such that the constant is 1/2. This is called normalized. So we have known that it's constant. So I can change f such that the constant is 0. So the Hamilton proves that this is constant. So I can change f, which does not affect here. So we still have this 0. Of course, a direct computation we have. So now I will prove a recent result due to Huaidong Cao and I, which is improvement of the estimate of corresponding result of Perman. So the theorem is for this complete non-compact soliton, we have C1, C2 constant depend on the geometry on the bore, unit bore, and n. Usually we don't say n, such that f x is bounded from above by r of x plus c2 square bigger than minus c1 square for sufficiently big. Actually, we can change a little bit such that for our Rx. Essentially, is this result. Perman proved that the estimate with constant here and with additional conditions such like non-negative curvature and bounded non-negative and bounded curvatures. So the good thing is that we don't need any condition, curvature condition, and also we have these two constants equals. That means that if you take some change of f, you have a function similar to distance function. Using this estimate, we can prove also a volume estimate. There exists a constant, also depend on the ball, such that the volume of geodesic ball x0 r is bigger than less than or equal to this. Again, this is so the volume is not is behave something like a Rn, exactly that classical example of Gaussian soliton. Remember that the Gauss soliton we have f equals to x squared over 4. So this estimate is sharp in the sense of this case. So it is important thing. Can we prove that problem that is it true that exists a constant c such that we know that the famous Calabi-Yau estimate for volume this question is related to this question. So during the proof, we will see that if you have an estimate from above, a good estimate from above, we can prove this kind of estimate. At this moment, the best result in this direction is Zhou and Zhou. They prove that the volume of M is infinite. So it's clear, the questions, the theorem and the questions. So the proof is not very long, but it's a little bit tricky. So I will give the proof. So let S0 be the distance function x. You fix a point x. We will prove that the distance function. So now Rx is just something like S0 now. Yeah. So we just denote this kind of. So you have a point here, x0. And then you have x here. So you will have geodesic gamma. Gamma is the normal geodesic with gamma prime equal 1. So from this notation, we know that he realized the distance. We can suppose that this is shortest geodesic, shortest. So we have this geodesic is stable. So we have I will continue to use the x. So for all phi continuous smooth function or local Lipschitz function that so it's so what we need is estimate f. So we can see that from the equation we have this function. This second derivative equals to d squared f gamma prime. So it equals to from this one, this half g minus Ricci. So we have one half minus Ricci x. So we have this equals to S0 minus 2 because it is the integral of second derivative. We just integrate from 1 to S0 minus 1. Minus Ricci x 1. I have somewhere. This is integral. Sometimes I don't put ds here. It's because it's arbitrary. We can take a function phi like this. This 1. This S0 minus 1. So we can take a function. Here's 1. It's 1. We take this kind of function. So if we take this kind of function, we can put square here because it is 1 on this interval. So we can minus 2. I just put 0 here. And because I have this, I need to put 0, 1. And or I also need to put 0 minus 1. Which x. I just have to put this. Actually, we have all the terms here. So if you look at the first term, we have this. So the integral of this kind of thing, because the derivative here is 0, so you only integrate these two parts. The derivative is 1. So you actually have, excuse me. There is a constant n minus 1 here because we use Ricci here. So we have minus 1. Here you have just make sure the constant. Actually, here I don't care about a lot about the constant. Yeah. So we have a constant here, 2n minus 1. Actually, here you only integrate in the unit ball. So it can be controlled by a constant depending on the geometry of the unit ball. So I can put the constant here, which depends on the unit ball. And we have this part. 0 y squared, which t squared. Again, we will compute this term, or other terms we have. If we have estimate for this, maybe we usually Perman and Hamilton they can compute this kind of thing. So they want to go to directly the estimate of this, but instead of doing that, we do this kind of thing, and we will see that exactly this is the right term we needed. So we can compute this term. So 0 phi squared, which x equals to. We use again the soliton equation, which is equals to 1/2 phi squared minus phi squared here is S0. This is a constant. This is because you have a square. So this is constant. I think it's 1/6, something like that. But it's square. So 1/f. So is this a constant? It equals to or what? So we do some integration by part here. It's S0 minus 1. 0. So we just put it in. This part equals to d. So we have f because the phi is 0 at point S0. So we have this term minus 2. We use the calculate derivative of this one. We have phi. Phi prime equals to minus 1. So we have this. Yes. S0 minus 1. S0. So the key point that we need to, we can find that this term is exactly this term. So we can cancel. If you put in, we can cancel these two terms. So if we can estimate this kind of this term by f at S0, so it is possible to do that because so then we have S0 minus 1 S0 phi. This is bigger than or equal to minus some constant. I don't care much about the constants here. Actually, the constant can be determined explicitly if you choose if you do some computations. So this we just put here. You have so this canceled. This also can be put in constant because it depends on geometry of unit ball. So we put constant here. So now we estimate this. We use again the equality. We have because R is non-negative. So we have F. Actually, we have this gradient 1/2. So that means F apply this one is less than equal to 1/2. So we have F S less than or equal to for any of course we have used again here we have you see this is again. So we have this one. It's bigger than. So we can put this one here, and integrate this. There are twice here. It's important. There's a twice here. So the integral of this is 1/2 plus times twice. We have F. F gamma zero is bigger than equal to twice this one, so it's bigger than minus constant. So it is. That is, we have, because this is exact fx, S0 is so the estimate from below has been obtained. Right? The other side is relatively simple because we have this estimate here. We have this estimate here. This implies you just integral. You have a estimate of. You have bounded from below. It's an integral directly some constant here. So it is immediate. So we have this estimate. It's not very difficult, but it's a type. We used frequently the equations, and we use the scalar curvature is non-active. These 2 points are important. So now I will give before give the proof of this theorem, I will give some corollary, which is useful in the next lecture. So since you have this estimate, you have volume control, you have a corollary. If you have a function u is bounded above by alpha r squared, where alpha is a constant below less than 1 over 4. R is a distant function. X here. Then U minus F is finite. In particular, if you choose, that means the weighted measure is finite. The total measure is finite. This has an immediate corollary, which has been proved by several people. First by Shumei Li, and then by some people. So it's the following: MGF, the shrinker, then the fundamental group is finite. It's an immediate corollary because if you take a universal covering of M, so you for each element in fundamental group you have a copy of M. So if you have n copies, so the integral of M tilde, you can lift the universal covering is continue to be a shrinking solid. You also can lift a metric and function, potential function. You have G, F here. So you have minus F, this which is finite, which is bigger than or equal to n plus. Of course, it's positive, it's finite, so n is finite. So the fundamental group is finite. It can also be used. Actually, it has been done by Mondialo. And Saison. Am I right? They prove that using this, they can prove the corollary. If for the shrinking soliton, the integral Ricci square is finite. It's integrable without any hypothesis. And why this is interesting, I will say that later. It is exactly the condition used by Peterson and Wiley. He said that if you have a conformally flat shrinker for any dimension, if this is finite, then they can classify. So that means that theorem don't need any condition. I will discuss the proof since I think it may be used for other cases, and in some sense it can be improved to determine the constant. The constant can be, if you choose the base point as the minimal point of potential function, the constant can be determined only depend on n. So it makes sense when you consider the convergence of shrinkers, Gromov Hausdorff distance of shrinkers. Any questions? Okay, so I will give proof of this as I said, this indicates that we can use a new function instead of using distant function, because distant function, if you use distant function, you get the estimate of Laplacian for distant function. You need condition of curvature. You need Ricci curvature condition or something like that. But here, if you define a function rho of x you have this equals to 1. The limit is 1. So you still have Laplace, and of course you have gradient rho equals to, which is parallel to f. So you have this kind of thing. If you can also compute the Laplace of rho, you have an estimate which is similar to like that. You can compute it's bigger than, less than or equal to rho n. So first I will prove to state the lemma. I define the wall, the disk is x of m, rho x. We define VR, which is volume, dr, which is integral of dr dv, and which is 0 to r, boundary of S. We use the Coyer formula, which d sigma ds. That means you have we also need a function dr, scalar curvature, which is also equals to 0r, boundary of S r over ds. So we also have a derivative of this kind of thing. The lemma is that just to make sure the formula. Four over r and we also have n. This is n. This is an interesting thing that you have r plus Laplacian f equal to n over 2. That means this is equivalent to, say, the integral of scalar curvature divided by the integral, the volume, dr, dv is less than or equal to. Remember that the estimate, the upper bound of estimate of upper bound of scalar curvature is important, but we don't have a pointwise estimate, but we have an average estimate for scalar curvature. Proof is, I will prove it that two results in the same time. We just put we have the r plus Laplacian equal to n over 2. So we have Laplace n over 2 minus r equal to Laplace f. We'll take integral on dr. This side is simple, just minus this side. This side we use divergence formula. It's equals to the boundary, the gradient f, the vector field, normal vector field of the boundary. So we know that this is a level set of function rho, or equivalent of level set of function f. It's equal to this. So we have gradient f squared over f over. So again, we use the r plus this one. So this equals to. So from this, we have already know that this is bigger than equal to 0. This part has been proved. So continue to compute. We have f minus r gradient f. So we have here f on the boundary. So we just we need the gradient f here. We have f equals to 1 over square. We have gradient f equals to 1/2 rho gradient rho. We need here. So this is 1 over half rho square. Here we have half rho gradient rho minus r rho here you cancel one, because on the boundary you have r, so you have here 1 over gradient rho minus, you have 2 over r, because rho equal to r on the boundary. So you have r gradient rho. So this is P prime. This is at prime. Exactly. We have claimed. I will see if I have time to complete. So now we will prove this result. We will use this lemma. And we compute this minus n e plus I did something. Oh, yeah. Seems strange. So, it's equal to minus we change it, we use this equation, so we have minus from here, we just integrate these two equations, and we need some routine computation of this formula. We have we combine these two terms. Two. So now we can choose R0 equals to square root so in this case we just we can estimate this term because that means this is negative, so we can put this out because we have the monotonicity of this chi r, because chi r, the derivative of chi r is increasing. This function is increasing, so we can bound this term by 0 and the integral of the rest of the part. We can put this out. So finally, we have it holds for all r bigger than or equal to r0. So when r0 is fixed, this is a constant. So this is order up to this. If you multiply this term, it will be a constant also. So so we have v of r less than or equal to n have this. Again, we use the lemma here because it's less than or equal to VR. So we can choose this are there when, for example, we only need we can choose the r is when r is big. So you can choose this less than 1/2. So minus, I just put the constant here. Half v of r. So you have vr to c. All right. So the important thing that we have to use this kind of thing. I think usually this is a usual speed I give the talk. I have 5 minutes. That's all.